All right, so now we're going to be looking at current density and a little bit more specific for those of you in AP Physics C. So basically, current is the rate of change. It's the derivative of the charge, actually. It's the rate of change that passes through an area of a wire. Um, that's generally how we would call it the current itself. And the average, and then so what's happening, right? These charges are moving at an average speed. We call the average drift velocity is the speed that an electron moves on average through the conductor. And so if you see like charge, you can think of it as like, oh, this is number of charges, right? Q is the charge of an electron. V is like the speed, right? The drift velocity, and then this is an area. Because like you could have like, think of it as like a pipe. There could be like lots of charges moving through a particular area here, right? And we want the total amount. And so the bigger the pipe, right, the more charges that can flow through there. Now the current density is that charge per area. So the way you think of it is the current density is the amount of current per unit area. So if you think of a conductor and you think of like, oh, we have charges here, 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 all throughout the area of this. If we divide by the area, that's the current density. Okay, so it's the current per area if you want to look at it a very simple way. Now, very often what's going to happen is that we're going to be given a current density function. Like this will be a function itself. And then so we have to set up this integral. We might have to split it into tiny areas and then calculate how much charge is moving through that area, kind of like we've done before when we use integrations, either in mechanics or like electric fields or electric potential, which we're chopping into little pieces. Now, there's a couple of things that are kind of interesting. Current density itself is a vector quantity, but the current is not. So you see this dot product here, kind of like if you think about the work is the integral of f dot dx here, right? Force and displacement are vectors, but work is a scalar. Right? This is a scalar quantity, and then these are vector quantities. It's a similar thing here. Its current density is a vector. It matters the direction that it's passing through it because it matters that the area you pick is perpendicular. Kind of like when we do Gauss's law, that the area is like perpendicular there to the electric field. We want the area to be that we do this integral over to be perpendicular to the current density. However, the total amount, the current itself is a scalar quantity. Now, it can be positive or negative, just like work can be positive or negative. Doesn't mean there's necessarily a direction, but this is an extra formula they throw in AP Physics C, just so you know. The electric field that causes the charges to move. Remember that it requires an electric field to cause the charges to move. That's why they're being pushed on by an external force, right? And so there's a formula here that relates the current density to the electric field, and it's based on the resistivity, which we'll talk a little bit more about later when we talk about resistance. Okay, so but the biggest part I want you to learn in this lesson is how do we set up these integrals whenever we have like current density. So let's take a look at an example. We have a long cylindrical conductor has a radius A, carries a current characterized by the current density J naught over R, where J naught is a constant and R is the radial distance from the cylinder's axis. What is the total current through the conductor? Now, so the density varies as a function of the radius. So what kind of shape do we want to pick when we're doing the areas? This is our area here, but we're going to chop it up into little rings. Why little rings, you might ask? Okay, so a little bit of thickness there, a little bit of ring there. It's because I pick a ring because everywhere along that ring, a distance r away, has the same current density because the current density is a function of distance from the axes there. So if I pick a very, very thin ring, see, I can't pick a very thick ring because obviously the density here is going to be different than the density here. But if I pick a thin ring, then the density is about constant over it because it's super, super thin there. So this ring has a thickness dr, okay? And then it has a little bit of area because there's some thickness there, right? And so we think about the probably the contribution of the current that's going through that little area is the J dot dA. And this is J naught over R. And what's the area of this? Well, so, we're assuming the current is going this way perpendicular to this area. So what's the scalar area of that? Is you think of it as like if you unrolled it as a rectangle, it would be the area of that rectangle, right? So if you unrolled it, this would have a rectangle with thickness dr, and the length would be the circumference of the circle, 2 pi r. So this would be 2 pi r dr. So the r's cancel, so you get 2 pi j naught dr is the amount of current through there, and then you're going to add them all up from r. What's radius? From we want all the little rings from r equals 0 to r equals a. So this is just a constant 2 pi j naught. This is going to be r from 0 to a, so 2 pi j naught times a. Okay, just like that. Let's look at another one here. We have a rectangular conductor is oriented as shown in the figure. The current density is given by the equation J of y is 2y squared, where y is the distance from the bottom of the conductor here. So this is my y-axis there. What is the total current through the conductor? So the density varies on this vertical distance. So what kind of shape do I want to cut into, slice it into, is probably a shape that's like this. That has a distance, that's a distance y away, has a thickness dy, and because it's so thin, the density is about constant over there, right? The density varies as a function of y. That's why we chop it up into something super thin vertically, because it's about constant over that little rectangular region, right? And so the contribution of the current through there is j dot dA. This is 2y squared. Now, what's the area of this little rectangular shape? It's w times dy. Okay, so this one's testing you to make sure you know what the direction of the area shape. Don't use L, W, because this distance from here to here is W times the height of that rectangle is dy. W is a constant, right? Because that's just the shape of the conductor. So then we're going to sum them all up from y equals 0 here, right? And then to y equals h, from 0 to h. So let's pull out the 2w. Those are constants. This would be y cubed over 3. From y equals 0 to h. And so that's going to be 2/3 w h cubed. If you plug in 0, you're just going to get 0. And that's going to be the total current like that.